my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So to conclude the equilibrium chapter, I wanted to talk about the response of equilibria to change. And this is called the Chatellier's principle, where basically chemical reactions adjust so as to minimize the effect of any changes. And so I'm going to talk about different changes that could happen to a state of equilibrium and how that affects the equilibrium constant as well as the reactant end products. So whenever I'm talking about any of these factors, just think of it like a balance. Basically, when something affects the equilibrium, for example, by increasing the reactant concentration or increasing the concentration of products, changing the pressure, changing the temperature, basically this balance is going to tip to a certain way, like whether products are favored, and so it's going to tip this way. But then in order to restore balance, Le Chatelier's principle is going to form more reactants so that it pushes it back up to a level field. Okay, so the first one I'm going to talk about is a change in concentration. And when we talk about the change in concentration, remember that the equilibrium constant remains the same and does not change. The reason why the equilibrium constant doesn't change is because a chemical reaction at equilibrium represents a fixed ratio of products to reactants. So when a reactant is added, more product will form until the original product to reactant ratio is attained, and so K remains constant. The same would happen if more product is added, more reactant will form until the original ratio is attained again. So what does this tell us about chemical reactions? It's the adjusting process. To minimize the effect of concentration change, it's going to tip the balance and produce more of the other thing to restore this balance. So let's look at an example. N2 gas plus 3H2 gas goes to 2NH3 gas. So let's say we increase N2 and we increase NH3, but we decrease H2. So how would Le Chatelier's principle restore balance in this scenario without adding more reactants, since there's an imbalance in the way the products and reactants are reacting? So how would we increase the yield of ammonia without adding more of these reactants? So Le Chatelier's principle also applies to changing physical parameters. So that's what we're moving on to now, such as pressure. So again, when we change pressure, the equilibrium constant does not change. But basically, a reaction can respond to minimize the effect of increasing pressure by decreasing volume. So remember that if the number of moles is held constant and concentration is the number of moles over volume, then the concentration would increase by decreasing the volume, right? And so in this scenario, let's look at this scenario again. Let's say K is equal to the product NH3 squared, since there's a coefficient of 2, over N2 and H2 cubed. Let's say that the initial concentrations at equilibrium was 0.1 molar for everything. So this would be 0.1 squared over 0.1 multiplied by 0.1 cubed, and we would get an answer of 100 for the equilibrium constant. If the pressure doubles, which means that the volume halves because of the inverse relationship, then the new concentrations would be 0.2 molar, right? So let's say pressure doubles or volume halves. then the new concentration would be 0.2 molar. And so now let's look at the reaction quotient. Reaction quotient Q is going to equal 0.2 squared over 0.2, 0.2 cubed, which is 25. And so the reaction will shift to the right. So the problem we had up here, in this particular scenario, if we have an increase in N2 but a decrease in H2, but we want to yield more ammonia, in this case, we can change the pressure. And by changing the pressure, we can look at the reaction quotient, and it says that it's going to shift to the right based upon the relationship between Q and K. So in this case, Q is less than K, so we can shift the reaction to the right. Okay, so another quick way to think about this is that when volume decreases and more moles of gas on the left-hand side, then the reaction will proceed to the right. On the other hand, when volume decreases and there's more moles of gas on the right-hand side, then the reaction proceeds to the left. So it's kind of the opposite of the side in which there's more moles of gas present. Okay, so if there's no change in concentration, there's no effect on the reaction. But there's also another way in which we can alter the equilibria, and that's by changing the temperature. So let me write number 3 over here, and this is finally a change in temperature. In the case of temperature, this is one of the few parameters where the equilibrium constant does change. So if a reaction requires heat, which is called endothermic, while forming a product, then heating it will favor the product formation because additional heat is used. So let me write that here for you, endothermic, additional heat used to favor product formation. On the other hand, if a reaction gives off heat, which is called exothermic, then the additional heat will be used to favor the reactants. So the way in which I like to think about temperature is that it's almost like adding another element to your reaction. So for example, let's write out the equation we were looking at before. In the case that heat is given off in the reaction, I'm going to put heat as an extra entity on the product side because heat is being released. So if heat is being released, it's an exothermic reaction. And since there's another guy on the right-hand side, this equilibrium is going to shift via the Chatelier's principle to favor the reactants. On the other hand, for endothermic, which is a reaction that takes in heat, now I'm going to use heat as almost like a reactant. It has to be on the left-hand side, to be an addition to the reaction. So in this case, now that I have heat on the left-hand side, it's going to favor product formation. And thus, for endothermic reactions, it's going to favor the product. So I hope that now you understand these 3 different parameters and how Le Chatelier's principle is always going to try to minimize the effect of changes in an equilibrium reaction.
Far away from the sun.